trying to give you sort of another dose of interesting viewpoints today, and you can see that it's not too complicated. But I promised from the beginning that we would try to study backward characteristics, right? I mean, the goal was to study, either, I mean, surely it's called calibrated curves in Wickham theory. Calibrated curves would be gamma from minus infinity to zero. First, well, let's change it. Let's lift everything to Rn. Okay. Uh, you know, again, with periodic periodicity, with everything periodic, and surely calibrated curves in PD we often call it backward characteristics. Okay, we have been we already so say we already used gamma, right? Used gamma dot and averaging to design matter measures, right? That what we did, and essentially we're trying to look at sort of like the the ergodic limit, or the last time average, to construct matter measures. But one of the questions that I provide, I promised to discuss with you is about a more classical question. This is more classical than the way to you averaging and passes to the weak limit via measures. There was a more sort of like a more um, classical question in the sense of asking about rotation vectors. Okay, the rotation vector is about whether you know I'm not asking about gamma dot. I'm just asking whether do I have gamma t over t as t goes to minus infinity converge to a rotation vector or not, to a vector q or not. So that's typically the first question in rotation vectors that people ask. The other question is inverse problem type question. They would ask that for any given vector q in Rn, can you find like gamma such that gamma t over t converging to q. Okay, so that's the second question. Again, I'm not saying about any gamma. I'm saying about gamma being backward characteristics. So those are the two main questions that people care about. And actually, that's kind of classical aspects. And then maybe the modern aspect about quantifications, right? About quantitative theories also. If um, you have gamma t over t converging to q, then what's the rate of conversion? Okay, so the third one is more modern, but basically it's belongs to various aspects in both probability, dynamical system, or PDE. Trying to sort of push forward that sort of uh, more quantitative and less compactness results. Okay. So it turns out that to study this kind of questions, I needed to wait until today because I needed to introduce the framework. And once we have the framework, then we are able to do it. It's not too hard, but but this kind of question about rotation vector is really dependent on what we had done earlier. All right. So in order to address this, this is not in Fatih's book, because in Fatih's book everything is about when you so in Fatih's book, he focused on C0, which is H bar 0. So only on this, and for, I mean, of course, you can shift things around, and the point that we PD people think that it's um, relevant, and surely same as we can theory is that we should try to think about all different variations of P. So we should think of C of big P, which is H bar of big P for all P. Okay, as I said, this is a very hard problem to understand. Up to date, there's just uh, a very few number of results along understanding H bar P or CFP SP varies. So it's really reasonable just to focus on C of 0. But when you put it in a broader framework, you're going to see that that's coming out naturally. Okay. So let me recall here, I mean, quickly, what's the algorithm problem, right? In P, again, it's written on the left panel, but I'm explaining. What you just need to do is that instead of thinking about the normal algorithm problem, this is a normal algorithm problem, right? Equals to C of 0. Then what you do is just you shift your Hamiltonian about with the big vector P, right? That's it, or you can, this is equal to CP or H bar P in the torus. Of course, I mean, this is still the same problem like like C naught, that's why because you can just define H of big capital P of XP just gonna be H of X capital P plus little p, right? And then it becomes uh the algorithm problem in P is just becoming HP of X dv X equals to CP, right? So there's nothing fancy about this. And but the interesting point now is that so typically here's sort of like a cartoon pictures of so graphs of H and H bar. This is just a cartoon picture. Again, things can be different, but here's one example that I know for sure. It can be like this. I have H of XP, just uh, like classical mechanics Hamiltonian. So if you draw your graph in P, it just a quadratic function, right? Now once you do this, you can write down what is the new Hamiltonian H bar in P, right? So it turns out that this is still convex. If H convex, then it's going to imply that H bar is convex. This we talked about earlier. This is the proof is very easy. But it turns out that after having H like this, you want to draw what's going to be the graph of H bar. Then H bar is not as nice as H. H bar is convex, but typically the general picture is that it's going to be a Hamiltonian H bar that has a flat part here. And H bar is not uniformly convex anymore. So, um, the hope normally in earlier was that H bar is nice, but it turns out that it's nice, but not, like extremely nice. It's convex still, but it has flat parts, and in general, it can be not differentiable at many points. And understanding the points at which it's not differentiable is still not yet done. Okay, not yet done deeply. There's some results. I mean, of course. I mean, we have good understanding in 2D, 3D higher, not really. Okay, so that's the viewpoint. But the key point that I wanted to present today is that we use H bar and its convexity to study back the questions about rotation vectors. That's a thing. That's why, you know, and again, I needed to wait until today. Uh, all right, so let me now go back to the lab panel. I'm recalling just HP is H capital P is this one, right? We shift everything by capital P. And then let's compute what's going to be the Lagrangian, well, for that shifted Hamiltonian, right? And then the Lagrangian L capital P, um, I never remember this formula. So, I mean, whenever I needed to do it, I just need to, you know, redo it, just tiny computations. But so compute the L capital P, it's going to be this formula, right? And then you um, just write back h of xp plus capital P, and then you change it to this one, and then you have to normalize it back. So it turns out that L capital P is just L shifted by P dot V, so shifted by a linear map, right, or whatever. Okay, so that's quite convenient. Okay. And as usual, you know, we have defined the backward characteristics for the algorithm problem at 0, and you can carry out exactly the same definition that you can define the backward characteristics for the problem at capital P. So you know, you go from any point T2 to T1, you pay uh, V is a solution to the algorithm problem. This is that V. You have the difference in values of V equals to the action, right? Action, but it has to be normalized, which is LP plus H bar P. And this can be rewritten down because of the fact that you see that I have the terms minus P dot V there. So this can be rewritten as just this one. uh, P is equals to the action, right? So that's very simple. Let me write down. So C is gamma is a backward characteristic of EP if for T2 less than T1 less than 0, I would have, you know, it's clear, right? Because if you look at the cell problem, you have like P plus dv, so it's kind of like p dot x plus v differentiating, right? You're differentiating that term, so it's natural that you have p dot x, which is p dot with gamma t1, um, plus v of gamma t1 minus p dot with gamma t2 plus v of gamma t2 equals just to the action functional, and I already moved P to the capital P to the left. I don't have to worry about that. So it's just the same action, Lagrangian. And the normalized constant is just H bar P, right? Yes. So same, nothing different. And you see, I wrote down the basic, I wrote down the basic questions here, right? I have to understand what's going to be the possible rotation vectors. If I have rate of conversion, if possible. The question about rate of conversion is widely open now. I mean, there's literally only one result that we got recently. There's nothing more than that. And also the inverse problem question. The inverse problem questions was a very classical question, dates back to the time of Poincaré. They often ask the question like, do you have, for any rotation vector, do you have sort of like a backward characteristic having that rotation vector? It turns out that the answer is negative. um, I'll tell you, but there's also some open question that I think that it might be true. Who knows? Okay, so great. So that's the setting. You see, now I'm ready to prove the following results. Um, Given gamma is a backward characteristics of the problem with EP, right? So exactly what I wrote on the right panel here. Maybe I should have said that this is an assumption here. Okay. So gamma is a backward characteristics of EP. Then I don't have conversion along the full sequence, but I do have conversion along a subsequence. So there would exist a subsequence going to minus infinity, so that I have the conversion of gamma tk over tk to a vector that is in the subgradient set. Okay, because again, our function is convex but need not to be differentiable, right? So what we are saying is that maybe your Hamiltonian could be like that. Oops. Your effective Hamiltonian could be like that, h bar, right? If you take this point capital P, then maybe this is Q that is in the subgradient of capital P, so that you have gamma tk over tk converges to Q, which is this rotation vector, right? Okay. So we don't have the full result that we have conversion along the full sequence, but we do have conversion along subsequence to a rotation vector, and a rotation vector is in the subgradient of the h bar. That's why I needed h bar to deal with this whole thing. Okay. Um, the proof is actually not too hard. The proof, again, once we have put ourselves in a good framework, then we are good to go. The proof is that we just use two points, So the 2 points that needed to use in the proofs was that, gamma is kind of optimal for the algorithmic problem at P, right? But gamma is suboptimal for the algorithm problem as any p tilde for any p tilde. Okay, that's it. Because optimality at p gives me that I have this equality, right? I have equality happens that the action equals to the difference in values, right? And then the suboptimality is exactly just saying, it exactly this thing is that we have been also using essentially in nearly every class, I guess, right? So this is exactly the gamma is optimal for ep, right? Again, vp is a solution to ep, right? Okay. And then the other part here is that we are using the fact that it's suboptimal for other p tilde, right? Suboptimal is we always have that the action functional is always greater than equals to the difference of values of that, right? Because gamma is a nice enough curve. In fact, it's ck here, right? So so this one is just that gamma is suboptimal, right? For e p tilde, for any p tilde. And surely we are dealing with differentiability, so we just need to take a small neighborhood. So take p tilde in bp1, and if you do so, then now clearly that you see the right hand side. Let me highlight the right hand side here. There we have the first part is the an equality, right? The second part is an inequality, but if you compare the actions, right, the action of the first part is just this integral, right? And the action of the second part is just this integral. It looks exactly the same. Just the difference is just h bar p and h bar p tilde, right? So therefore, when you compare them, when you take the difference, then you can see that that when you take the difference, you see that h bar p tilde minus h bar p pops out naturally. That's just so beautiful, right? And then when you subtract the left hand side, the compare the left hand side. So let's see what's happening with the left hand side. The left hand side, what's most important is gamma zero is a fixed point, right? So I don't care. This is, let me just write out what's the most important thing. It's gonna be p dot with minus of gamma minus t, right? V is a bounded function, so everything is bounded. So plus O1, okay? And then the second terms in the second part of the left hand side is p tilde dot with minus gamma of minus t plus O1. Again, V p tilde is bounded, and again gamma zero is bounded. So you see, once you do that comparison, when you do subtractions, then you can see right away that you have h bar of p tilde minus h bar p is going to be greater than equals to, uh, I hope that the size that I wrote is correct, p tilde minus p, uh, uh, yes, dot with gamma of minus t over minus t, um, minus O1 over t, something like that, right? So that's what you have. And clearly that, what is amazing here is that surely you see that h bar p tilde minus h bar p pops out, p tilde minus p pops out, right? And then I have this quantity, which exactly resembles the last time average. So you see that last time average comes into the game very often and very naturally, okay? And and you see that gamma dot, gamma is ck in fact, right? And its velocity is bounded. So you can find a subsequence so that you have gamma tk over tk converging to q. So when you pass the limit, right? So you take, you let here, you let uh, t equals to tk, and let tk is, yeah, minus t going to minus infinity. Some, the sorry about this t and minus t switching around. I would have that uh, gamma tk over tk would converges to q, right? So then I would have that h bar p tilde minus h bar p is going to be greater than equals to p tilde minus p dot with the vector q. Okay, so clearly this implies that q is in the subgradient of h bar p. So we are done. Okay, so you see, I mean, this proof is nothing new. It just based upon the fact that you know, we need to consider the whole h bar to prove this thing. If I only consider the value c of 0 or h bar of 0, I wouldn't have the whole h bar. I wouldn't be able to, like test around and um, shift things around in order to have use the optimality together, it's suboptimality at other points to get these conclusions. But once I have that, this proof, you see that there's nothing new here, right? I mean, it's just a natural thing to do, right? And I have conversion, so essentially that's what I promised, and then it's just done. The proof is, you know half a page. Okay, so let me pause here for questions or concerns or things you want to discuss with me. Anything of interest? Okay.
So basically, if you know in advance that at that point H bar is differentiable,
Mhm.
then you have conversion in the whole sequence. So it's kind of ad hoc.
Yes. Yeah, it's ad hoc because exactly that. So the problem of H bar is that it's not it's not too nice. In fact, that sometimes that this although that is it's differentiable, but almost everywhere, but the sets of non-differentiability can well be something like Cantor sets or something complicated, right? So we don't know a priori what's happening, so that's why it's a bit bad. um, but it's true that if you have H bar is differential at P, then you have conversion for full sequence, but there's no known rate of conversion. So yes, so yeah, so exactly that's actually one point of the remark I made, that if H bar is differential at P, then you would have conversion along full sequence, and this is exactly a compactness result, right? Because you just do it for all possible subsequences, so you prove by contradictions. But here it's already that what's gonna be only when you only assume that H bar is differential at P, then what gonna be rate of convergence? Okay, again, um, you see that a lot of important points, important directions can be asked by first simple questions. You see that although this kind of question I'm asking you can be very simple, um, and it can be two case scenarios, right? I mean, the first case is that you solve the problem and then it's not related to the ideas are not related to other directions, and we are not lucky to develop a whole framework. But sometimes if you are lucky enough, you solve the problem and your ideas can propagate and build up another layers of the whole area. And that's that has happened. So I'm quite optimistic that there should be new layers of understanding, and the whole sort of like area should be improved, not just sort of here and there. Um, okay, and then if H bar is not differentiable at P, then there's still this simple but important open question. I asked Fatih even you or others that I don't see yet this problem, this simple question being written down, that if you have H bar is not differentiable at a point, right? So clearly in this case, in the second remark here that say H bar is not differentiable here at this point capital P, right? And then let's say that I have two different rotation vector Q1. Yeah, my drawing is not good. This is gonna be capital P, and you have two rotation vectors Q1 and Q2. And the question is that then can you find an example and two different sequences that they converge to two different rotation vectors, right? So that's open. I had a very um, artificial example that sort of like that this thing holds, but then in my example H is not differentiable, and Yifan told me it's cheating, the question is that you assume that H is nice, is C2 and everything, and can you still find this kind of example showing that you have conversion to two different limits? That's important because it shows that, in fact, uh, the thing is very delicate. Okay? Um, Very simple. I mean, very simple to pose. It's not that simple to do, right? Okay, so let's see. I have other remarks, but let's see if I should do this one first. Yes, let maybe let me just do this one, and then and then I'll get to the another point I want to talk about. Okay, so for the rate of conversion question I asked earlier, we only have a partial result here, and believe it or not, this was the only thing we knew up to now. This is 2021, and this is the only thing we know up to now, and then surely there some this is taken from a paper by Mitake, you, and then also related results in Gomez results. So I mean, so um again, if h bar is, because h bar is convex, right? So by Alexandrov theorem is twice differentiable, right? Again, the sets of the points that is twice differentiable can be very bad. I mean, it can be missing stuffs around. And here by twice differentiability, I mean that so if so uh, h bar is twice differentiable at p, if essentially you have the Taylor expansion, right? So you would have h bar of p tilde minus h bar of p plus d h bar p dot with p tilde minus p plus 1/2 d square h bar p tilde minus p uh, p tilde minus p. That whole thing is going to be less than equals to little o of p tilde minus p square. Right? That's a Alexandrov theorem. Um, yes, surely the proof is quite complicated, but anyway, um, um, what we can prove is that if h bar is twice differentiable at p, then we have the rate of conversion gamma t over t minus dh bar p is of the order cp over t to the 1/2. Okay, and this actually, it's a very important result that allows us to rate is c over t to the power 1/2, but c depends heavily on p. Okay, um, and as simple as it looks, by using this, and we can connect the dots and get to prove optimal rates of conversion in homogenization theory, and that was essentially an open question for 30 years. So what I mean is that sometimes if you are lucky, you start with something simple, but once you build up the framework and you can connect the dots from something very different from dynamics to something like homogenization that was in PDE, right? And actually homogenizations, I mentioned quite sometimes, is related to, or essentially it's kind of the same like first pass speculations in probability. So they are very distant frameworks, but once you can connect the dots and bring things together, uh, it's beautiful. Yeah, so the proof of the theorem is very simple, and this is the best we can do at this moment for the general setting, and I hope for more. But okay, so what do we do? Well, I mean, uh, what do we do? Uh, it's not a big deal. It's just quantifying the above result, right? The above result gives me that gives me this box that I'm putting here, right? So yeah, maybe let me write. So from the above qualitative result, what we see is that we can compare the value, right? P tilde minus h bar p is greater than or equals to p tilde minus p. Okay, so here for some reason I keep gamma. Oh yeah, fine. Yeah, I'm being not being consistent. Sorry about that. Sometimes I throw gamma zero away. Sometimes I keep it. Okay. Minus c over t. Okay. So this is the early result, right? I mean, and then if we pass the limit naively, then the best we can get was just a qualitative conversion, because here h bar is already differentiable at capital P, right? But you know, there's just a little bit more here that we can exploit, is that we can control the left hand side, right? By the fact that h bar is twice differentiable at at capital P. Okay, so in fact, I mean, to be honest, what I'm using here is only C11. You know, not really more like more. I'm just using h bar is C11 at capital P. I'm not using C2 because I'm just using the fact that h bar of P tilde minus h bar P is less than equals to, you know, I'm doing tile expansion, right? So it's less than equals to dh bar of P not with P tilde minus P and plus the next order term. So I'm just going to write as C times P tilde minus P square. Okay. So just exactly a tile expansion. And of course, you know, you can say that, hey, you know, I don't need C11. I can also do the result for C1 alpha. That's true. If you have C1 alpha, you have certain rates. You know, but the main question is, if it's only differentiable, can you get a rate of conversion, or can you prove that the conversion is as low as you want? Period. You know, that's something. Okay. So if you do that, then you can see that you have you know, dh bar of P dot with P tilde minus P plus C of P tilde minus P square is going to be greater than equals to P tilde minus P dot with the rotation vector, right? Minus C over T. Okay, so you have that. And now that, you know, you can combine things together and again, just choose it appropriately. This is essentially Cauchy-Schwarz type inequality, whatever, right? So you combine together, you just see that you have the difference of gamma t over t minus the rotation factor. You have p tilde minus p here, and then you have two error terms, right? You have this one is the first error term, and this one is the second error term. And then again, it's just Cauchy-Schwarz type inequality. You choose p tilde, you know, smartly so that it captures exactly the rate, right? Um, because again, I mean, Cauchy-Schwarz tells me that it's, you know, p tilde minus p square plus 1 over t is greater than equals to p tilde 2 times p tilde minus p times 1 over root t, right? Um, of course, you know, so that tells me that the best I can get is that rate 1 over root t, right? And that's how we do it. If w is 0, then we are done. If w is not 0, then you choose it exactly in this manner, because we knew that 1 over root t is the optimal rate, you know, in this manner of Cauchy-Schwarz, right? And you do that, and you can see that uh, the vector w is this one, right? Uh, it's less than c over root of t, and we are done. Okay, it's nothing complicated, but I haven't been able to prove anything further than this for the general setting, and I welcome new ideas. You know, so let me pause here for questions or concerns before I address the last point that I didn't write down here.
So I have a question. So in 1D, let's say if you can have like a nice ODE formula for gamma t, right? If I'm correct, then can we write gamma t over t as an integral, average of integral of gamma dot,
Mhm.
and then using some sort of averaging integral? Has that then it done in 1D?
Yeah, one D is done. Yes,
Uh,
one D is integrable, right? So I mean, I actually you actually I think you did it also in your first paper, but yes. So one
yeah,
D is, yes, absolutely. It's exactly what you mentioned. So you have gamma t over t minus hp h prime. So in one D we are lucky. H is differentiable everywhere. It's exactly less than c over t, and this is exactly corresponding to this is sort of like a quantitative quantitative version of the ergodic problem, of the ergodic theorem or something. Absolutely, what you said. Yeah. Um, one day is based upon I cannot recall. Yes. So one day, if I remember it correctly, based upon this result. So this is equivalent to the following, which is I think that all of you here are familiar with equivalent with this result, that you have f is a function mapping from R to R that is one periodic. Then you would have this result. Remarkably, so this is exactly what Sun was saying. You have 1 over t, integral from 0 to t of f x dx. You subtract its average. So average of f is integral from 0 to 1 f y dy. Okay. This is going to be less than or equal to c over length of t. It's really beautiful because in one day, what is remarkable is that in one day, right? I mean, what people say that is integrable is that you are trapped. You have no way to go. You can just go to the left or go to the right. So, you know, um, absolutely, yeah. So thanks. Yeah, I should have said that in one day we have this result. In 2D we also know a little bit more. I'm cheating. I'm not saying, but when n is greater than or equal to 3, nothing is known. It's known except except the above partial result. Okay. Yep. Does it answer the question? Or?
yes, yes.
Yeah. Great. Okay, so here's my belief. So my belief is the open question is that it could be the case, in fact, that say it should be that 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 one can find examples of h that is C2. Again, I said earlier I have one example that h is not differentiable, and that's sort of cheating. That h is C2, and h bar is differential at p, and the conversion of gamma t over t minus d h bar p is as low is conversion to 0 as low as we want. Okay, um, that's my belief, and it's quite complicated to deal with parts. There's a famous also Arnold diffusions along this line of sort of dealing with parts, and then sometimes that this corresponding to instability of the parts. But yeah, I'm not going to talk about that. So in the last few minutes, 5 minutes, so let me just tell you one thing that I didn't say here, that about the questions about rotation vectors, right? that do we have all possible rotation vectors, right? And the sort of, this is the inverse problem, right? Is it possible to obtain all possible rotation vectors? And the answer is no. Okay, so I don't have time to this, but I refer to the Hedlund example, Hedlund example in the book. Um, so what it says is that the example is that we are in 3D, and 2D is different. We have not a lot of space, but in 3D, you can construct the problem quite easily. Again, I can describe it to you. You can think about the problem this way. I am creating three highways in 3D. Each of the highway is just a single line, single rod. So it's like this, and this is the first one. The second one is like this. They are all perpendicular to each other, and the third one is gonna be non-intersecting and perpendicular to each other down here. Okay, so those like three non-intersecting, perpendicular to each other. Okay, so lines, and you can assume everything is periodic. I'm not worried about this. And the problem is actually very simple to understand. You can also think about this in terms of geodesics in geometry, in Euclid, and Riemann in geometry. But the proof is there in the book. It's not hard. You now have all the knowledge to read it. The way I'm thinking about this is that you assume that your speed in each of the freeway is one. Okay, so you have speed one in each of the freeway, speed one in all these lines, three lines. Okay, and you assume that your speed is epsilon outside. Okay, of course you can create a narrow tubes around the freeway, and you do a cut-off functions that you have that is decreasing really. So the speed is sort of decreasing from 1 to epsilon on the tubes around the three lines, and then the speed is epsilon outside of the three lines. Okay, so that's sort of, you can think of it as a traveling problem, front propagation problem, right? So you are traveling on this three-dimensional space. If you are outside of the tubes, you go with very slow speed, just epsilon. So the best way for you to do is you hop on those freeway, right? Those are the geodesics, and exactly they corresponding to the lines in the matter set or the Aubrey set. So the geodesics are the ones that you travel really fast. And in this case, in this example, it turns out that the matter set is equal to the Aubrey set. It's just these three lines, okay? And moreover, it turns out that we can only obtain that for any possible optimal parts. Um, so let's say that this is in the directions of E1, right? This is the direction of E1. This is the direction of E2, E3. So moreover, the velocity is only converging as t goes to minus infinity to a vector q that is one of these three value only. Okay. Um, so that means that things, we cannot obtain all possible rotation vectors, and that's why this made the paper of Hedlund very famous. And of course, I mean, this is a very interesting example. It's already, this was done in 1940 or 1938 or 39. Nearly 100 years ago. It's a remarkable result. Um, you know and you can think of the problem really naturally in terms of imagination, right? You can only do this in 3D because you have more space to put. Actually, um, you can put a lot of lines there that are not intersecting. just that you need that their direction rational, so that they create a periodic orbits. If they're irrational, they're gonna cover the whole, I mean, they're gonna be dance in the torus, whatever. So I do refer you to read this example and see that the question about the inverse problem is not true, right? However, here's another open question that I want to pose. It's this one is going to be vague because I don't have time for that. But I want to say that you can create uh, uh, approximate approximate backward characteristics, or you can think about approximate optimal parts, and then can we have gamma t over t converge to any possible q for any admissible or possible q. Okay, so that's the question, and I believe the answer is yes. I don't have a proof. Okay, so I'm being very vague here. Let me tell you what do I mean by approximate backward characteristic or approximate geodesics. Here's what you do, right? So you say that, okay, it's boring, right? If I just follow the three freeways, then it's just taking me forever. And I can only obtain the three rotation vectors E1, E2, E3, right? However, you can always do a convex combination of those to get any vector that you want, right? With speed less than one. And how do you do it? Well, I mean, like, what you do is that you would go from in E1, for example, for quite some amount of time, and you would pay a little bit of the price to jump from E1 to E2, and then go in E2 for some amount of time, whatever you like, and you can hop back and forth. The actions of going back and forth is very expensive, right? Because the velocity is very, very slow there. But like, this is talking about going for infinite amount of time, right? So I can afford to pay a bit of the price um, to do that. And then if I think about approximate backward characteristics or approximate optimal parts, by sort of creating a combination of those in such a way that then I can obtain that at the t over t can converge to any vector q that is in the convex hull of e1, e2, e3. So in other words, the question shouldn't be about real geodesics, but about approximate geodesics. Then with approximate geodesics, you can probably obtain all possible rotation vectors. And in fact, in PDE, in a lot of problems, we only need approximate backward characteristics. So this is very vague, but I just want to throw it out to end the class. And I'm grateful that still, yesterday we had a student seminar, and my student told me that there was some problem with the voice, and hopefully there's none today. And then I'm happy to end it. And thank you all. And then you know just finish whatever you need to finish, and have the class done and your semester done. And and then have a good summer, supposedly. Okay, any quick question for me before we end? Questions? Okay, so other than that, and again, thank you all for being patient. I'm trying my best. I know that this is not easy, and also it feels weird to talk to the screen all the times and whatever, but um, yeah. Right. So thank you, and again, enjoy it. And again, you should stay safe and healthy, but you should also try to have a good summer ahead. Don't feel bad. Maybe after grading and everything, after next week you are done, and try to spend it nicely. And I'm also um, last year and also this year I have absolutely no plan ahead. I just cannot plan it because like what I'm gonna do is it so it's a weird time, but we also need to be careful. So um, thank you, and yeah, email me if you have questions or any concerns, and that's it for the class. Okay, bye for now. Maybe see you in person next semester. Well, I'm not teaching next semester, but later. Okay. Of course, I hope to see you in person soon in your talks or whatever. Okay. Bye. Thank you.